All right, we are live. I think we are. Welcome everyone to our 17th Ocean Plastic webinar, already 17th, so I'm quite happy with this. And we are all. I am Audrey Asson. I am the EU coordinator for the Geo Blue Planet initiative. And today we have with us René Garello. René is, oh, sorry. That's my bad. Sorry about this. I will remove it from the the replay video. Anyways, we have René with us today. He is working for EMT Atlantic, which is an engineering school in Brittany. He's been also the, yes, and he's been the president for 4 years of the IEEE Ocean Engineer Society. Is also the co-founder of the plastic initiative of this IEEE, and is also the co-founder of the marine debris working group of GeoBlue Planet, which I have the pleasure to lead with him. So René will give us today a presentation about plastic monitoring, all the techniques that exist that are available right now, and what are the pros and the cons for all these monitoring techniques. And it will give a 30 minutes presentation. And after this, we'll go on to a live discussion like we always do. You can go to Slido, so sli.do, and then it will be you will be asked an hashtag key, and which is OPW, like the Ocean Plastic Webinar. And yes, we'll have 30 minutes questions, and at noon, we'll wrap this up. So without further ado, René, if you can share your screen, and the floor is yours.
Okay.
All right, we can see your screen. I think you need to click again on the...
Okay. Good day, everyone.
Yes, it's perfect.
Okay. Okay, you see then my screen. So
we see your second slide, yes.
My second slide, okay. That's my first slide. So yeah, as Audrey said, I'm René Garello, and I will talk today. The title was found by, I have an echo, so just wait a minute because I can't. Yeah, I'm confused because I'm hearing the Zoom and the at the same time. So just 1 second, I come back.
Sure. Is there any way I can help you with anything, René?
Okay. I don't have the echo anymore. So starting again.
All right, no worries.
Okay, that is a good start, I think. You hear me there? Okay.
Yes, we can hear you, but we cannot see your screen.
You cannot see the screen. Okay, so
no.
That is, sorry for the stupid mistake I made, but now it should be okay.
Yes, yes, it's perfect.
Okay,
can
sorry.
You hear the echo again, or it's fine with you?
No, it's gone.
Perfect.
So, okay, the title, The Available Measuring Techniques for Marine Debris, a review, was proposed by Audrey, and so I've worked around that. As she said, I'm a professor at IMT Atlantique in French, and as I'm retired, I'm now emeritus, and I'm also a life fellow at the IEEE, and I've put the names of several persons that I used with consent the some slides or some informations. So what I'm going to talk about is first the context of what is observation for marine debris and monitoring for marine debris. And of course, we talk about observations from different means, different sensors, either satellite bonds, which was the idea that comes to everyone when we talk about marine debris on the ocean. Say, oh, satellite, they can see everything, which is not exactly true, but we talk about that. And of course, in situ measurement and even underwater measurement. And finally, once we have observed and monitor and possibly tracked, what can we understand of that? And from this humongous amount of data that is going to be available, and then of course, the processing is going to be involving data processing, signal processing, machine learning, etc., and the buzzword artificial intelligence. So context. I'm displaying there a slide that I picture an artist drawing, as we said, that I used from after a conference that was given in 2012 in Yuzu in Korea, and by the JAMSTEC representative, and at this time was talking about future plan for ocean research. And in fact, he put the emphasis on all the sensors that you can see on the screen. You have sensors, I put blue and red dots, meaning either the sensors or some other kind of observation, data processing, communications. So everything is connected in a sense. From the satellite, you can observe, you can transmit, you can see from the ground. Also, you can process, and of course, underwater, you have also many devices, and some of them can also measure effects of plastic, especially underwater. It's more the microplastic that will be present. Saying that, and when you observe, you cannot disconnect what you observe from the reality of life. And that's why I picked this very interesting slide showing that, especially for the ocean, the Earth and the ocean is it's very complex. And so whatever you observe, you have to take into account that it's not still picture, it's moving. There are everything that goes from evaporation, of course, of the ocean to rain, which can affect the measures, especially for radars. You have also the underwater motions that can move, of course, the body of water and then change the trajectory of whatever is on the surface, and especially in our case, the plastic. So we have to have that in mind, that this is something that is complicated. The data, that's a picture that we picked, a colleague and I, from a source, which is the plastics in the marine environment, and in 2017. And so you see that the plastic that you see in the environment can be from floating, of course, on the ocean and landing on the beach, but also in water column here. Oops, I'm too fast with my mouse. And okay, go back. And also present in the marine organisms like fishes and so on. So that's present everywhere. Once that is said, how can we do something? That was a question the community asked itself several years ago, not so many years ago, but so I tried to summarize that into, yes, we can observe, but what are the challenges? The first part is that, or the first observation, or the first comment, is that almost all of the plastic flowing in the ocean is coming from rivers. So it's already an indication. And of course, from the river mouth, it also goes directly on the beach and in the ocean. And so we can, at this level, process with direct measuring of plastic concentration, via in situ sampling at the water surface and or on the beach. So in order to have a kind of a very good idea of the amount of plastic. Then we have all the other means that, which I was talking about earlier, about the sensors, and that's the direct measurement of either the plastics or the motion or the movement of the surface, and that is what is called remote sensing. When I was very young, in my first job in the States, my boss said, "You want to know what is remote sensing?" I said, "Of course, yes." And he said, "That's whatever I cannot grab with my hand is remote sensing." So you see the amount and the variety of sensors that we can imagine. So I try to list many of them, probably not them all, but this is a way to see what we can use. Okay, it's not because we say we could use that it's possible. So of course we can have in situ observation. We can have in situ directly at the level of the sea surface, or with field surveys and drones flying over. So the surface is quite small in this case. I mean, the drone, even a very modern drone, cannot observe a very large surface. We have also, and more, the crowdsourcing. That's whoever is taking a picture, or that is an individual, a citizen, or an association with the aim of doing exactly that, going and taking picture. We have other indicators which are still indirect. For instance, the coastal and watershed population. So it's an indication of the potential of plastic that goes to the beach and the ocean. The characteristic of the beach, characteristic of the bathymetry that may indicate how the waves are coming and going, and then bringing or not, or removing plastic. We have some sources from the traffic, the ship traffic on the ocean. Remind that about 99% of the traffic of goods is borne by ships from on the ocean, so it's a large number of ships. We could also, some people have developed sensors which are automated, and I show an example for in situ measurement underwater. We have a potential with HF-based, ground-based radars. So an HF radar is also covering not a very large surface, but there are networks of HF radars, especially in the United States. And they can, of course, they cannot see the plastic, but they can see the movement, as I was indicating, that is in the remote sensing part. And of course, we have a big potential about monitoring the via satellites, because that is covering a very large surface. Then the problem is a bit the opposite of the ground-based, that is, the surface is large, but the revisit time is not excellent. And also from space, the main problem is resolution. In order to see, to have a very good resolution that is below 10 meters, we need to have satellites which are not civil right now. So what I'm going to talk about, and that's this, I'm showing my screen, but you cannot see my screen, of course. So you see that it's based on a paper we produced for the Oceans 2019 conference in Marseille 2 years ago, and presented there. So, okay, I'm going to show a different types of information that could be gathered. This one is from a group in Spain, later, and they were showing in a workshop 2 different sensors. One that is kind of what they call a lab sensor, and that could be put on a ship or an underwater autonomous vehicle, something that is much smaller, and that's a European project, ODC, and that could be either inserted on an autonomous underwater vehicle, or in this case, a glider. The glider goes through the ocean and gather information, and especially on microplastic, meaning that there is a big need of developing filters in order to select what kind of micro size is needed. Is it under 100 microns, over, etc.? And that is quite complicated. And this is one example. There are so many that I just picked this one of the collection of plastic and on beaches, and not only the collection, but also the identification, possibly identification of plastic, and a possibility of tracking back where the plastic is coming from. If you detect, if you pick something on the beach and you see the plastic is what it is, but if it's a bottle or equivalent, there is an indication where it comes from or where it has been produced. It's not because it has been produced somewhere, I don't know, let's say in China, and I'm not saying that it's always in China, that it goes all over the world, but it also indicates what kind of ships, for instance, was putting the trash away on board, and you see many different sources, and all the countries of the world can be on the same beach. Okay, if you want to ask questions, you have to go to Slido key-OPW. I was supposed to say that at the beginning, but okay, I say it now. So now we look directly with the sensors, observations. So the rest was in situ measurement, opportunity, citizen data, lots of data already, and much more coming in because observation, we have satellite, and because I am in France and in Europe, I picked only the European ones. There are, of course, other countries in the world having satellites, but I focus on this one. In Europe, through the Copernicus program, we have the satellite Sentinel satellite family. And up to now, we have 6 in the family, and each of them has 1, 2, 3 versions. Just to indicate what they do, what kind of sensor they have on board, I have a slide which shows that exactly. So, and I will indicate which one we can use. The Sentinel one is mainly imaging radar. So it's an active sensor, it sends a wave and gets some return back. Sentinel 2 has what we call multispectral high resolution imaging. High resolution means about 10 meters. Okay, it's not 1 meter or less. And multispectral includes visible also. Sentinel-3 has sensors which are dedicated to, for instance, sea surface temperature, sea surface height, ocean color. And the 3 of them, 1 to 3, can be used directly or indirectly for plastic, let's say, observation, not direct, but as I was saying just before, the movement or some related parameters. Sentinel-4 and 5 are directly related to atmosphere, so far it's not, we are not using them. And Sentinel-6 is as an altimeter, which we will be able to use because it in the end it reconstructs the motion of the currents. Among other things, and I've put a here a link, but it's easy to find about Copernicus and the Sentinel family, and there are all descriptions that you want to have. So just to image what they can see, for instance, I mean the satellite and the sensors. they can detect the temperature of the surface, which is very important to see fronts, for instance, so to see some information or to get some information when mixed with the sea surface height of the currents. Ocean color, which is also a good indicator because not only chlorophyll can be seen, but also the influence of the plastic through this chlorophyll or also plankton, etc. Sea ice, so far, we don't use that for the plastic. The color, the true color, meaning that it's like a photo from a camera. And using the radar, we can see the winds and the waves, the sea level anomaly using the altimeter, the SAR, the synthetic aperture radar, coupled with some information on the winds from scatterometers, gives information, yes, again, on the wind, but also on the waves and the currents, so the motions. And also, using the synthetic aperture radar, we can, through a kind of model, have an access to the salinity of the surface that is directly or indirectly, in this case, related to the roughness of the surface, which is the only thing that a radar sees. All the rest is modulation of this roughness or absence or lack in English of roughness. Then you have something which is smooth, and in this case it can be a lack of wind or an oil spill, or maybe some floating debris, but you don't see the debris, you see the lack of information at this place. So it's always a second order observation in a sense. This is a picture that, of course, you find zillions of pictures like that, and you can say, oh yeah, if I have a satellite, of course, I'm going to see everything. This is a bit it's not fake news, of course, but it's a bit a misinformation because you don't see accumulation like that on a very large extent, especially in the middle of the sea. The concentration, let's say very often we heard about the seventh continent, the patch on the Pacific Ocean, North Pacific Ocean, but the density is very small. I mean, it's about a few kilos by square kilometers. You don't see that. So anyway, observing can help us find some places where there are some accumulations, and for that, as I said in the beginning, and it's my main way of thinking, we need to gather and to put together all the information that is, for instance, the observation from satellite of the currents, the observation from in situ sensors of also the currents or other parameters, and of course the models of circulation on the ocean that predict that if you have this kind of currents and this kind of motion, then the plastic is going to accumulate somewhere with a high probability, and then you can go there and do something. But we need to combine all this information. That the main word is synergy between sensors and models, and synergy between sensors, models, and the physical, let's say, presentation or explanation or understanding in terms of geoscience. So, to go back to the characteristics of the sensors, as I said, the satellite remote sensing is only possible for the observation of the floating debris. We cannot see through the ocean. The SAR is very interesting because it's very high resolution and it gives information, as I said before, on topography, from the topography to the sea surface roughness, indicating the winds and the waves, and we can have correlation with the movement of marine debris. We cannot see the plastic directly. The radar wave, which is a microwave, goes through You can see it. But we can couple, as I said in my previous slide, with the circulation on the ocean. We can use also altimeter to reconstruct the path of plastic from the source to its fate. And we need again to combine with data sets that are available somewhere else, okay? Either from another satellite, either from an in situ measurement, but as I said previously, we need to combine all that together. So, for instance, a possibility that I was presenting in this talk in Marseille is, for instance, the use of altimeter to have all the information on a very large scale on the surface, that is not only the topography, but also the currents. And something that might work, it's not yet in place, but we have also on the surface a lot of buoys or drifters and sending their information to a communication satellite, which so far is quite expensive and very slow. Sorry. So that could be a possibility, and this is what is indicated in the next slide, not at the beginning, but in the middle of the slide. Some groups were thinking of having direct tracking of the plastic or floating pieces by putting these small tags, sending information, some GPS tags. Of course, we need then something that is different from a Iridium communication satellite, and the same groups also started to send, and we have seen that on the previous year, constellation of very small satellites, CubeSat. For instance, the Kineis constellation, and that constellation is not 2 or 3 satellites, it's hundreds, even thousands. I've seen recently that for telecommunication, there were 3,000 satellites sent that for 5G everywhere in the world, including the ocean. This is a bit different, but that's another means, the possible source of information, and we can use it for plastic, not only for 5G communications. Of course, that means that you have to put on the plastic something else, and so it's another trash that we put in the ocean. Okay, the risk-benefit associated with. But this is something that, in my opinion, is part of the future observation and tracking, monitoring tracking of plastic. Coming back to the satellite sensors, recently, the last 2 years, I've seen several papers, even the presentation here in this YouTube by Loren, and also some papers by Kostak Tozopoulis about the use of what we call multi or hyperspectral and ocean color, and looking at some anomalies or signatures and combining that with, because the resolution is very poor, combining that with drone survey or airborne sensors, airborne meaning on plane. So several papers have been produced recently, one also from the group at ESA in Italy. So that's a field that at least have a lot of research going on, and in my opinion, that is going to produce results which are goes in the right direction. And again, so far we don't have really a complete answer and complete solution. An example that was given to me by Shungu Gabarat, that's an example of the detection of plastic here, and that was the ocean cleanup project. And then with a drone, you see an enlargement here, and then you can pick something that is larger, of course, with a satellite, but you need to have a drone there. Okay, so finally, I still have about 5 minutes. Understanding that, okay, so how do we observe? I talk about that. The main part is how do we integrate? We have a diversity of sources. We have information from a lot of information from above and also from below the surface through, as I said, the underwater vehicles. We have observation on the beach from citizens. We have models. We need to integrate that. We have also diversity in communities, so we need the communities to communicate and to talk together. And also we have a diversity of data processing. There are several platforms. We have pre-processing, post-processing. Lots of people say, especially the geophysicists, okay, well, where is your calibration? How is it calibrated? So if you take a picture, nothing is calibrated, of course. So how do we manage that? And that's exactly where the artificial intelligence intervenes, is that it's made for taking into account the fact that the data per itself is not calibrated, but the amount is so large that you find some kind of correlation, it's not the right word, but information. For that, the idea is to what we call the data model loop, that is something that is not driven by a theory. That is, we have a theory, we have hypotheses, and we observe, but driven by data. We get the data, we observe plenty of data, we make hypotheses, and then we have a theory possible. So that's an example that was given to me by my colleague at IFREMER, and that was mainly for underwater measurement, but taking into account some satellite images as well to have the information from above. And doing this loop, it's possible to accumulate the information and have, which I will show in the next slide, send it to some kind of, let's say, artificial intelligence, and then have the artificial intelligence sort out, in a sense. So from something that goes from the models and the monitoring and talks together, and we have so far the artificial intelligence, let's say, processing the data and indicating that, okay, by combining that and that type of answers from a sensor, I can have this kind of information. Next step is to go a step beyond and say, okay, the artificial intelligence is also going to talk to the models in order for the models to include whatever is hidden somewhere in this large amount of data, and that's more than petabytes of data. It's now petabytes, whatever, 10 to the power of 18, even more now. So it's not for the human individual to compute that. You need to have some kind of help or guidance. So 2 slides, because that's just the end. Machine learning, I don't want to have let's say, a review on machine learning. It's just that somewhere you have the real world and you have sensors and measuring devices, and through a kind of process, which sometimes is a black box, but I try to develop that, and I picked this very interesting book here about machine learning. In the end, we can have, through classical statistical analysis and other analysis, image processing, and so on, we can have some results. And I've seen a very good article very recently from this colleague at ESA and working the Phi Lab at in Eswin near Roma, towards detecting floating objects, etc. And they use exactly that with their observation and the Sentinel-2 data. Okay, so concerning the artificial intelligence, and that's one about my last or almost last slide. Finally, we have 3 main drivers. We have data and big data, and everyone says we need more data. We don't have enough data because we need to have data on this plant that was not observed, on this plant that was not modeled. So increasing again this petabyte of data every month or every day now. We need to have models, of course, and then better and better and algorithms. And we have, this is my colleague from computer science. He said, hey, you need also to have some processing power. If not, you cannot do anything. And we added something to that, which is from the designer point of view, we need something that we all have, which is us, or at least our brain. Okay, because artificial intelligence is doing what we said to it to do. So in order to finish, one example of something that we have started, it's not yet, we hoped to have research power on that, is gathering everything I said. For instance, this is a map of a circulation in Indonesia given to me by Christophe Maes and I can't remember her first name, Dobler. This is a model, okay? And combine that with all the observation from satellite in situ and etc. And we can, using artificial intelligence, guide some kind of not so futuristic boat here that is going to gather all the accumulation of plastic and transform that in energy or something else. And that's from the sea cleaners with whom I'm working. So in closing, and I hope I have not been too much above my time, 30 minutes, it's okay. I would like to thank the partner that I've been working with since 2017 or so. So, of course, the IEEE Oceanic Engineering, because they provided what we call an initiative and fundings. The Blue Planet from Geo and Audrey is the representative of the Blue Planet in Europe. The WWF, because they work with me on providing a lot of background information, and NOAA with Emily Smale. And just for the fun of it, if you want to know what is AI, artificial intelligence, it's not an autonomous machine, and it's not what's so-called an intelligent machine. It's something different. Questions?
Thank you. Here we go. Thank you, René,
okay.
for that.
I stopped sharing my screen.
Yes, I think that would be great. And now we're going to move on to the questions, if that's all right with you. Thank you for the presentation. So we have quite a few questions on Slido. So if people arrived a little bit late and are not familiar with how we do it at OPW, you go on the Slido sli.do website, and then it's going to ask you for a key, and the key is OPW. And you're going to land on a web page where you can ask questions, but you can also actually vote for the question that you would like to see entered first. So for now, I have no specific question that comes up first. So I'm just going to go in a chronological order. And I really like the first question we have from Tom. I think it's a little bit of like, can you just, so the question is, what is the question that you are trying to answer with this data? So I think it's a little bit of like in one sentence, like what are you trying to monitor with all this data that you have?
Okay, good question. What I'm trying to monitor, not only me, but is the floating plastic and debris. I mean, we talk a lot about plastic, but we have also other like fishing nets and so on and so on. So the idea is that how can we do that? So, of course, from a technological point of view, we have, as I explained, all the sensors and so on, the models. And so the aim is to be able to detect where the plastics if they are not on the beaches, are. That is, they are somewhere on the ocean, and we have two solutions. Either first, they are so scattered that, okay, what can we do? I mean, it's just then a mean of trying to, let's say, estimate the amount. And if there are accumulations, which the models from the geophysicists, that is the ocean circulation models, shows that we know that they accumulate in some places, there are not so many. Okay, so it's accumulate, it means that even though that it's not like let's say a complete surface that you can walk on, still the density is large enough so that you can collect them. So that's the second idea, and that's the aim. At least something I'm working toward is trying to guide this. I was showing the boat from the sea cleaners. There are also other boats like that, and guide them in order to collect the plastic to do something with it. Okay, sea cleaners, it's kind of a floating plant, and they transform that into energy. But you can also collect that plastic and and bring it back to somewhere on the beach or to a recycling plant.
All right, thank you. So from what I understand, what you were saying is that the main reason is understanding the global distribution of plastic, but there is a more practical reason that is guiding the cleanup processes and so on.
Yeah,
the next question.
Okay, go ahead. No, I wanted to say that I don't know if it was behind the question, but doing this kind of research, there are two aims. The first one is to advance in the understanding of research. The second is try to find solutions in order to solve a problem. And I'm more on the second side.
That's very engineering of you.
Which I'm not, by the way, but
but you're in an engineering school.
I'm just an old professor, you know.
The second question is it possible to reconciliate the data from the different monitoring methods that are applied in one same area?
Reconciliate, that is, in terms of... No, I understand.
I guess it means that can you use all the different data that you have in one area to make the most of it?
Yeah, that's of course that's the aim, and that is also the problem, because from the, as I said, from the geophysicist, geoscience community, they want to have sensors or devices in the ocean or not that are able to give an answer of what they measure, which is calibrated. That is, if they say whatever number, they say 10, it means 10, more or less something. And but if you have just information from different sources which cannot give the answer 10, it's just something that is observed and is added as an information. And then in this case, it's not the precision of the information that is important, it's the amount of information that is important. Mm-hmm. Just to make a parallel with something that I've been working with a bit in terms of telecommunications. You know that all the communications in the world are monitored. Okay, we are monitored. I mean, there is something in the United States called the NSA, and whatever you send on Twitter, it's the reality. I mean, we know that. So whatever you send on Twitter or Texto or whatever is monitored, and they are looking at keywords. So the information is not the precision of the keyword, is the accumulation of keywords. The example I was given, and maybe it's not true, but for instance, they knew when bin Laden was killed, they knew that something happened exactly at the place where he was killed, because so many tweets with the keywords that were connected to bin Laden accumulated at this place in Pakistan. So you see what I mean? It's that that was not any precision at all, but so many things that, hey, there is something there. That's
But maybe one day we'll get that many information on marine
exactly
as much as
I hope so.
as the text. I think it goes in line with like the following question, which is how do you make sense of having different type of data, meaning weight, surface, number of pieces, like every monitoring system gives you a different information. How do you make all of this different information into one information that you can use?
Okay, again, a very good question, because that's when I started working on this, not this field of plastic, but observing the ocean surface, I did it from my background, which is signal processing and mathematics and statistics. So the real life was not so important at this time, so-called real life. So, and I very rapidly was talking with my colleague in the geoscience world, geophysicists, and they say, okay, you measure that, and you make a kind of a correlation, or but it makes no sense, because that doesn't exist in real life. And so that's when I started to understand that I needed to combine with models. That is, if I observed, let's say, on the surface, and that was part of the question, is I observed the temperature of the surface. The models indicate that if I combine somewhere with the height of the surface, then I can see let's say, try to predict the motion of the flow of water going from one height to another, and because the temperature is different from hot to cold, or conversely, then you have a flow, and then gives information on the current. So I'm not measuring the current, I'm measuring two different things, and I put that together. And that's all the trick, if I could say so, that you need to combine all this information, but you need to know what the information means in terms of geophysics. If not, of course, I could come up with a model which is, again, I'm not going to talk about my past, but when I started to work at NOAA, I was working on the atmosphere. It's different, but my colleague made models and ran very complicated models on that, at this time, very powerful computer that was just sitting there. And in the morning, so that was powerful, but long time to compute. And so it was computing for a day, 2 days, 3 days. And very often he came back on the third day and say, hey, I blew the world again. It exploded it, because my model is not very good. So I can come up with a model that blew everything up, but that's not reality.
All right, and I guess artificial intelligence is definitely another way of putting different data that don't talk to each other.
Yes.
In a statistical, meaningful way.
In a sense, yes.
Yeah. The following question is, are there any study reporting floating plastics observed by hyperspectral sensors?
Yes, if the resolution, if the plastic floating is large enough to be seen, so the actual resolution from Sentinel-2 or equivalent satellite is about 10 meters, what we say 10 by 10, okay? Mm-hmm. So it's either a very large plastic. We have satellite, the world, the humanity, has satellite that has a very higher resolution, meter-like, sub-meter, but they are military. So they can observe plastic, but they are not really interested in plastic. But yes, we could, yes, of course. So that is a very good question, because what can we do? Okay, if I have a piece of plastic, or let's say something floating, which is about or below that resolution patch, I will more or less see it, but not exactly. So I need to have another source trying to give me an information on the effect of the plastic on the surface, which has a larger extent, so that I see from a larger extent, or a larger surface, that there is something that is there. you know, exactly the Ben Laden stuff I was talking about. There is something there. And then I can put that in database and combine with other things like drones or planes and so on. And then that is kind of synergy that may be the answer. Of course, in the middle of the ocean or in the middle of the Pacific, you don't send a drone.
Have drones.
Not really.
All right. Then we have a comment from, I'm going to say it in French, but Robin, if you're not French, I'm sorry about this, from Robin de Vry. Okay. Thank you, René, for highlighting some of the UAV data from the Ocean Climate in the Pacific. There is another recent study from us where we use AI to sort large amounts of image data. So there is the link in the slide if people are interested. We'll go on to the next question, which is, do you see there being a type of spectral imaging, that allows specific characterization of plastic in terms of polymer types or degradation state?
I don't know, but I see what you mean. That is a hyperspectral means that you divide the spectrum in so many bands, like hyperspectral can go up to 256. And then if there is a signature of the plastic in a given band and it is not absorbed through the atmosphere, then we have the signature. That's my understanding.
And the different polymers have different signatures. That's right?
Yes, yes.
Okay.
But then it's not my field, but I know a bit when I talk with my colleague from biology or chemistry that they, especially for the microplastic, they can identify, the different types. So
in the lab.
In the lab, of course.
Yes. Yeah, of course. And actually, this one is related, I think. What is the best in situ sensor that can measure microplastic concentration underwater?
There are several that I have seen, and again, it's a bit aside my field. I've seen no processing, but I talk with people. So I don't know the best, but I know that the people working in they work on mainly filters. The main problem is that the filters must be very fine, of course, in order to just gather, let's say, 100 microns, but also must be very clean before, in order not to be contaminated, because we have plastic on us, So if I take the filter and I insert it in something that goes into the ocean, I have to be sure that I have not put any plastic already on it, which so that's a difficulty. And I've been not monitoring, but watching or reading about different European projects, and so far it's this kind of device, and it's on some kind of carrier that's either, for instance, a boat that goes on a given path, for instance, from Roscoff to Plymouth. That's where I am, not Plymouth, on the other side. And then gathering back and forth, or specific AUVs. I've seen recently a paper using autonomous underwater vehicles with of course, a sensor like that. And so the underwater autonomous vehicle, you can give it a mission, so it goes exactly, more or less exactly where you want, and when it's back in the lab, then you get at the same time the trajectory and the result of what he has accumulated in terms of plastic, microplastic.
I see. Then we have another question from Tom. Is asking if your conclusion is that sea-based sailing collector as sorry, is your conclusion that sea-based sailing collectors are a possible solution? And what is your conclusion about the data you've seen from the sea-based sailing collectors?
Okay, what I've seen from the sea-based collector, I've seen one in action as a demonstrator, not a big one from the sea cleaners, a smaller one, which is something like 10 meters long and able to gather at the same time macroplastic, so bottles and stuff like that, but also some, let's say, net, again, with a mesh, which is small enough, kind of microplastic. So it works, and the project just they're not the only one. The one I know is different. So they are very large boat, Manta. I'm not making any publicity for that. It's an NGO anyway. Is aimed to that. So it's prospective. I mean, we live in a world where if we want to be at the front end of research, we need to do things that are innovative and possibly not feasible. It's the beauty of research that you don't know in advance that you're going to come up with a solution. Okay, but anyway, we have because we try to work together. We have the firm belief that it is possible, and from our side, that is the side of let's say research and operational research, by combining, as I showed, by combining the models, all the information that we can to add to the circulation model on the ocean, that is putting other in situ sensors near the coast or at the river mouth, and information from satellite and so on. We can show that the probability of an accumulation at a given place is high or is above whatever %, and then the boat goes there and does what he is supposed to do. Okay, that's the only answer. That's research. You know, I cannot say. And being a statistician, I cannot say yes or no. Possibly, yeah.
Yes, yeah. So I think that's a good place to stop. It's 57 on my clock. And I would like if you could give some concluding remarks, I think, about the IMDOS, the Integrated Marine Debris Observing System, and on the the UNEP global platform for the global partnership on marine litter, because I think this kind of like falls like exactly into what you were saying, that we have a lot of data and we need structure to, you know, gather all this data and to analyze all this data. So maybe you could tell us a little bit on the IMDOS and the GPML platform.
Okay, yes, in my mind, they are complementary. IMDOS, which is the Integrated Marine Observing System, marine debris.
Yeah, you missed the debris.
It's exactly what I was presenting. There are many ways of observing the marine debris and constituting databases. Okay, now the databases, they must be related. We are not building silos. They must be related. They must be connected to some kind of data management, data processing, which is more the GPML, the global platform for marine leader. And also, as I was showing on one slide, that is, we must have a return also from, let's say, the GPML, saying, yeah, okay, that's fine. We have databases with information. Can you get information there? And can I go to, let's say, the citizen data people, that is beach cleaners, and ask them to send more information or complete the information? And so that is part of the GPML which is connected to with IBM with an interface for the beach cleaners where they use their mobile phone or smartphone and are related, and then they can talk to the platform. I know it's a bit futuristic, but not so much, because that's basically what we do. Many people do when they live in a bubble inside their Facebook and or equivalent, and they share information. That's this sharing of information. If it is guided by a platform with an artificial intelligence, why not? I mean, but that's my view.
Yes. All right. Well, thank you very much, René, for a really interesting talk and really interesting questions. Thank you to all the viewers we had. We will see you all again in November for the next, which will be the 18th, and I still can't believe it, the 18th Ocean Plastic webinars. And that's it for now. And I think we can go offline. Thank you again, René, for your interesting talk and stats. Thank you.
Thank you.